Hello! Today I'll explain some of the concepts and principles behind Gumbuya that make this application platform so unique. Gumbuya is a full-stack software-as-a-service platform for developing and delivering software-as-a-service applications. The primary objective is to simplify the way we build and deploy applications. And we do this not just by removing all the infrastructure intricacies for being a cloud service, but also by taking an entirely new approach to the application development model. Our unique approach allows a radical reduction in time and resources for building and delivering applications compared to the conventional model. I will explain this new model now. So let's see how Gumbuya is different from other platforms. Most solutions available in the market had followed an evolution path over previous waves, but they are all based on the same principles that were present in the first computer systems. And although we've seen significant improvement over the years, fundamentally, they've all been applying the same computation model. Gumbuya is based on a complete new computation model, a new form of computing that is more aligned with the type of application that we're building today. To better understand this, let's first look at the traditional computing model, the one we've been using for decades. When computers were first built in the 40s, they had a unique purpose: to calculate. They were machines that could solve mathematical problems in a fraction of the time that a human could. And for many years, even after they became accessible to the private sector, computers were still mostly used for this purpose: to calculate. It was only in the 80s and the 90s, with the appearance of the personal computer and later with the internet and now with the mobile devices, that we started to see a new type of application. These new applications are much more interactive than calculation intensive. But the computation model for building these applications remains the same. The current computation model, optimized for calculation, is based on arithmetics. And the root cause of this is because at the core of the processor inside the computer, an LAU performs a very limited set of arithmetical and logical functions, executing them many times to solve very complex algorithms. And this is the model that all solutions that we've built since the 40s have followed. We have since been using a sophisticated calculator to develop applications. The programming languages we have been using to program our current applications have no alternative but to follow the same principles. So we write code using mathematical and logical functions to describe the processes we want the applications to do. These programs will iterate over information following these mathematical and logical functions to achieve the results we want. Most applications use relational databases to store their information. They can perform operations on massive amounts of information, stored in the form of tables in a high-performance computer. But they perform the same mathematical and logical functions to gather the information and send them back to the application. And there's nothing wrong with this traditional computing model, as it has been, and perhaps will continue to be, the most efficient model for applications that need an enormous amount of calculations and data manipulation. It's been so successful that we have been applying it to develop all sorts of applications, including the ones that don't need calculations at all. But today's applications, like social business applications, e-commerce, booking systems, inventory and service management, compliance management, wealth management, just to name a few, do not use calculations that much. They are more interactive and model-driven applications, based on user input and decision-making, rather than calculation. You start with a small set of information that is contextually relevant to what you're willing to achieve, and then you make a decision and take an action, and move to the next interaction. Some calculation might still be needed during the process or at the end, but in general, it represents a small portion of the application. Then why use a calculator to develop the entire application? So let's take a look at Gumbuya's computation model. We call it semantic computing, powered by a virtual graph CPU that runs on a high-performance computer in the cloud. Similarly to the LAU in traditional computing, Gumbuya's graph processor performs a very limited set of semantic operations many times to achieve the desired result. Instead of arithmetics, our semantic CPU uses set theory, a branch of mathematics logic that studies sets, which informally are collections of objects or things. Combined with graph theory, which are mathematical structures used to model pairwise relationships between objects. By storing information in a graph, instead of the traditional tables, Gumbuya can provide a multidimensional view of information. Now, we're all familiar with sets, as we seamlessly use them on our day-to-day, making it much intuitive to describe how our information is organized and how it will move around along the process we intend to build. Each node in the graph represents a thing, like a product, a person, an event, an image, just anything. And each thing is described by a schema. In this way, we can represent anything that can be described by a set of attributes like name, description, price, dimension, color, category, whatever. Gumbuya provides some predefined schemas for the most common types of things, but you can create your own custom schemas to accommodate anything. Now, these things can be related to each other by a connection. There is no limit in the number of connections one thing can have. These connections or relationships can be named according to their meanings. So by analyzing the things and their connection names, you should be able to understand the semantics of the information. So for instance, if you have a thing type product that is connected to another thing type video with a connection name called video of the product, you can tell what this thing video is all about. As anything can be described and manipulated in this Gumbuya graph, it makes it very easy for smart devices to be part of this, enabling endless scenarios for the Internet of Things. To represent sets in a graph, we use a particular type of schema, like collections or conversations, that support a different type of connection. These special schemas can have what we call the inside connection, that represents a contained type of relationship. Therefore, a set can be defined by all the things that are connected inside a collection, different from the outside connection that represent a semantic relationship between two things. In this example, we have a product that is connected to a collection of related images. It is also connected to a video and a conversation. This conversation has many comments that are connected inside the conversation. Another way of representing a set is by the name of the semantic connection or relationship between things. For instance, if the semantic relationship that connects two individuals is called spouse, you can tell that they are a couple. So by using a common relationship name to connect things of a similar type, you can form sets. Now, semantic relationships in Gumbuya are directional. They go from the connecting thing to the connected thing. Therefore, there is no information on the connected thing that it relates to the connecting thing. For that to happen, another connection has to be explicitly created. The connections are directional, as they can have different meaning, read semantics, from the perspective of the connecting thing. We must then carefully choose proper names to describe the relationship between things, as these relationship names will determine how the information will be used in the application. In Gumbuya, not only the information is stored and processed by the semantic computing processor, but the applications you assemble are also handled in a similar way. In the Composer, Gumbuya's tool for assembling applications, we start by selecting a canvas, which is the digital surface that will host the application. To the canvas, we connect layouts. We can nest as many layouts as we want to build our interaction. To each layout section, we connect a component, or an information visualizer, that will render the information. Each component can have one or more actions that they will execute on the information, so we connect the desired actions to each component. And then we connect the information to each component. Additionally, we can connect a style to the experience, a context, and a user access rights. The end result is that you eliminate around 80% of the coding, as most of the logics are semantically described in the graph and does not need programming. Programming is limited for building user interfaces like components or visualizers to visualize things, and for those few parts where calculators is still required, or for building integrations with legacy systems or third-party systems. Solutions are then assembled rather than developed. The few parts that were coded are highly reusable, as they are now just drag and drop where needed. Custom schemas and custom visualizers become part of your IP assets, as they can be used over and over in new versions or new solutions. The application responds to the information and their semantic relationships. Any change in the graph will immediately be reflected in the application. The assembled applications become a grid of interactive experiences that can call each other based on user interactions. At every step, the user will make a decision based on the current set of information, take an action, and move to the next interaction, just as we do in our day-to-day activities. So now that we've covered how to represent information in the semantic graph, how do we organize the information in sets and build semantic relationships, let's take a look at how the semantic computing processor works when creating an application. So very much as in the traditional model, where the processor repeatedly executes a small set of arithmetical and logical operations very efficiently to achieve an outcome, the semantic computing processor also performs a reduced set of graph operations to produce interactive experiences. These graph operations are create, attach, update, and detach. And the best way of demonstrating this is by applying this concept to a known scenario. Let's get a booking system, for instance. It could be any booking system, but for our example, let's get a taxi booking system as we're all familiar with one. But I'll use a simplified model just to illustrate some of the concepts that we've just covered. Let's first define a taxi. A taxi is a combination of a vehicle and a driver. So a driver described by its own schema connected to a vehicle also described by its own schema will define a taxi. The semantic CPU executes only 4 operations to create a taxi. To add a taxi to the fleet, it takes only 1 operation. Adding an additional customer takes only 2 operations. So the information architecture of our taxi booking system will look somehow like this. We will have taxis formed by a connection between a driver and a vehicle, as we described before. They will be grouped in a set called fleet, which will have subsets of the fleet, showing which taxis are available and which taxis are hired. We will have a set of registered customers. We will have bookings, which will connect a customer to a taxi when served. They will be placed in a set called bookings. These bookings can be organized in 2 subsets, the ones that are waiting and the ones that have been served. Additionally, we can have a set containing historic information where each customer and each driver will have its own set with their booking records. If your taxi company grows, all you have to do is create supersets of the sets that we had and just expand. Let's now take a look at the interaction architecture. This is the taxi booking application itself. We will take a look at 4 scenarios: creating a new customer, creating a new taxi, booking a taxi, and closing the booking. The first scenario is create a new customer. This is instantiated by an interaction of the customer. The customer will then fill up his information and save. This will just create a customer based on the customer schema and will attach that information to the customer collection. 2 operations. Creating a new taxi. Again, like we said before, we have a taxi is comprised of 2 things, a driver and a vehicle. So the driver will then fill up his information, hit next, which will create the driver information based on the driver schema. It will then pop up the next interaction screen, which is the vehicle. It will then fill up the vehicle information, save. This will create a vehicle based on the vehicle schema, and will attach the vehicle to the driver and attach the driver to the vehicle. And finally, attach this taxi to the fleet. A booking. A booking will start with a customer interaction. The customer will fill up the booking information and place the booking. This will create a booking based on the booking schema. It will then connect the customer to the booking and connect the booking to a waiting collection. The driver will then fetch the waiting collection. An external system can be used to filter up the bookings that are close to the taxi. The taxi will then select one of the bookings. It will then detach the booking from the waiting and pass it over to the serve, which will trigger a notification for the customer. It will then detach the taxi from the available and place it on the hired. Closing a booking. When the passenger is delivered, the taxi driver will notify the system. This will disconnect the taxi from the hired and connect it to the available, making the taxi available. The passenger will then pay. By doing so, this will disconnect the booking from the served and attach it to the history. It will send notification for both the passenger and the driver, and it will also connect the booking to the historic data of the passenger and the driver. As you can see, with a good information architecture that semantically describes your business and a good interaction design centered around the user and the usage of the application, we can build a solution just with 4 semantic operators and a few lines of code. Developing an application in this way does not seem too complex, does it? Well, it is not supposed to be. But we got used to the complex and lengthy development process, while the real value is in the business model and not in the application. With the traditional development model, we spend far more time and resources building the application rather than perfecting the model. It is this that Gumbuya is willing to change. You can then rapidly develop and deploy applications. In a matter of hours, you can convert an idea into a working mockup, test it around, and in a few days, you can perfect it into a prototype. The same prototype can be refined and enhanced over a few weeks, evolving into a pilot project. If the pilot project results are positive, it can be deployed on a larger scale, or go through a new iteration cycle until it's ready. So now that we have learned some of the concepts behind Gumbuya, I'll show a quick demo to see how all this comes alive in the Gumbuya suite. When you log into the Gumbuya development environment, you will be first exposed to the modeler, a tool for manipulating the graph in a more familiar way, resembling a finder or a file explorer that we use to organize our files in a file system. The information in Gumbuya is organized into episodes, which are supersets of information. You can create as many episodes you need to accommodate your information architecture. Inside an episode, you can create any type of information, including subsets in the form of collections. As you can see in this taxi episode, where we have 6 collections. You can create information at any level inside an episode. The modeler provides some predefined information types to pick from, as well as some schemas for the most common information types. But you can also create and publish your own custom schemas to accommodate your needs. So let's see how the information is organized in some of these collections. Let's look at the customer collection. As you see, we have 4 customers connected inside this collection. Now let's take a look at the drivers collection. We have 3 drivers connected inside this collection. And now let's look at the fleet. As you can see, inside the fleet, we have 3 other collections. One containing all the cars in the fleet, and we have 4 cars here. Another collection containing the available cars, and one containing the cars that are busy. You can nest collections as you do with subfolders in your file system. So let's go back to the drivers and create a new driver, as we intentionally left one extra car in the fleet, if you didn't notice, and it needs a driver. We will use a predefined contact person schema for the driver. We will upload a photo of the driver, and we will call him driver green. We can now connect this driver to its car. So we'll use the connect pane to navigate through the repository to the fleet where all the cars are and select his car. We will name the relationship car and confirm. So our driver green is now connected to a car. But the car is still not connected to the driver. Remember, the connections are directional. So we will create a reverse connection from the car to the driver, and we will call this relationship driver. Lastly, to complete the new driver information, we will also create his historical collection, where his booking records will be kept, and connect it to the driver using the relationship name history. Now, all these steps we just did via the modeler console to create the driver, its related information and semantic relationships will be performed by the application. The modeler is a tool for building and changing structures and testing information architecture, not for populating the graph. So before we move to the next tool for building applications, let's use the modeler to traverse through the information via the semantic connections. Let's start with a customer. Let's get William, for instance. As you can see, he is connected to his historical collection by the semantic relationship called history. Inside his historical collection, he has one booking. This booking is connected to William by the semantic relationship passenger, and to a car by the relationship car. Now the car is connected to driver John by the semantic relationship driver, and driver John is connected back to the car and to his own historical collection that contains the same booking. So I hope this gives you an idea of how to create information structures that can describe anything, and how this information can be connected to each other via semantic relationships to build sophisticated information architectures that can describe your business model. So now that we've seen the modeler, we will take a look at another tool that we call the composer for building applications. In the composer, we assemble interactions called compositions that can call each other to form complex applications. In this demo, I will create a simple customer creation interaction. We start by defining a digital template to be used. In our case, I will select an elastic or responsive canvas. We then give the interaction a name and we edit the interaction. The first step is to connect a layout according to the information we intend to work with. I will use a row stack, and I will place a small banner in the first row. So I'll use a fixed size layout and set the height to 60 pixels. I will then leave a space for the customer information input in the second row. The next step is to connect the components or information visualizers that will manipulate the information. In the top row, I will use an image visualizer to display my banner. And on the second row, I will use a form edit component for inputting the customer information into the graph. I will then add a bottom banner, similarly as I did on the first row. Now that the layout and components are connected into the canvas, I will connect the information. I will start by connecting the banner images that I had previously loaded. I will then configure the component to display them as I want. Next, I will connect the customer schema to the form edit components so the component will know what information it should gather. This component allows you to configure what information should be visible, as well as what fields are mandatory or read-only. I will also make a small change in the button icons to add some aesthetic. The next step is to connect some action components that will determine what actions will be available for the interactions to use. I will use a connect action to connect the output of the form edit component, which I've already connected to the customer schema, to the customer collection. So I'll set the destination of the connect action to the customer collection and tell it to connect whatever it receives as an input from the calling component. I will now configure the action of the form edit component for it to call the connect action when a form create or submit is issued. And I will configure the cancel action for it to go back to the calling interaction. I will also set up the action of the connect component to reload the same interaction if the connection action is successful, and to go back if it fails. Finally, I will connect a style to the interaction and set the style prefix. I can now test if this interaction works by selecting the preview. I can either use the QR code to test it on a mobile device or use the URL to test it in a new browser tab. I'll first test the responsiveness of the interaction to see if it responds well by changing the size of the screen. I will use the modeler to go to the customer collection to see if the interaction will in fact do what it is intended to do. So I'll open the modeler on a new tab and go to the customer collection. I will then use the interaction I just created to add a new customer. I will call him Fred Smith. I'll fill up his information and submit. There he is, connected inside the customer collection. Fred can now start booking taxis. The Composer is just one of the ways of assembling applications in Gumbuya, as this tool is still in beta and under development. But Gumbuya provides an extensive library of components, snaplets as we call them, that can be used with HTML, CSS, and JavaScript to build interactive applications. Gumbuya's components library can be used in conjunction with popular JavaScript and CSS libraries or frameworks, like jQuery, React, or Bootstrap. The modeler and the composer that I just demoed were entirely built with Gumbuya, using these libraries, and are delivered through the Gumbuya platform, just as the applications these tools produce. And I hope this gives you an idea of how sophisticated a Gumbuya application can be. Gumbuya is served through a combination of two of the world's leading cloud service providers, Microsoft Windows Azure and Amazon Web Services, leveraging on their combined reliability, scalability, and security to deliver a world-class service. As the infrastructure is entirely abstracted, you never have to worry about it, so you can focus on building your application. Gumbuya is offered either as a public cloud or a private cloud. So if you're planning to build a software as a service application around a new innovative model that you have created for a particular segment or to fulfill a specific demand, but you're not willing to become a software company to offer it, Gumbuya can certainly help you achieve this way faster than you thought. We provide not only the platform, but also professional services that can help you achieve your results. Thank you very much.